Cool. Thank you so much, guys. Can everyone hear me? Okay. All right. So yeah, this is kind of the precursor to deep learning, and it's going to be a fairly animated introduction. Animated introduction to machine learning. Cool. So hi, I'm Kerryn. I'm a humanities baby for life. So I studied philosophy and economics. And basically I'm up here because I really enjoy learning and I really enjoy PowerPoint animations. Yeah, so I think as the world's data grows, so does its aptitude for AI. And I think that means that a lot of people have a lot more opportunities to get involved in the conversations around AI. I don't think that necessarily means that you have to code and be part of the AI journey. I just think it means that you need to understand what's happening and how it affects you. Great. And in saying that, I think a lot of the ideas that come out of AI are super powerful, but are often exclusionary because there's either a language barrier or you don't quite understand how the computation side of it works. And if that's the case, then I think AI is not doing a good enough job of being accessible. Cool. So yeah, you are in the right place if you like AI, or if you want to like AI. You want other people to like AI too, and you like stories. So this is basically what I'm going to cover. So just very high level. I don't want to get too much into like the technicalities of the coding or the maths or the stats. I think a lot of that can be read online. But just the A1s of kind of what different models are, how they're used, etc. Then I'm going to go into story time, which is really just an instantiation of a couple of the models. And then we're going to go through a new hit series called AI's Next Top Model, which is hosted by Tyra Banks. And then finally, some tips and tricks that I've learned over my AI journey. Cool. All right, so basically, what is AI? And I guess holistically, it's the union between computer science and statistics, right? Just kidding, it's not that. Basically, it's a computer or a machine's proximity to being human and how far away or how close a machine or a computer is to being human. And essentially, we can kind of classify it in two different ways. So in terms of like the actions that an AI or a computer has, this is referred to as type 1. So right now, we're in the stage of weak or narrow AI, which really just means we're able to solve narrow, very well-defined problems. So like a chess game. So you'd have to feed in a whole lot of data and a whole lot of kind of solutions for it to gamify the system. Then we get to strong AI, which we're not there yet, we're getting there, and it's basically the ability for a computer to act like a human. Okay. Then the other type, this refers mostly to the functions of AI. So right now we have reactive machines. Well, not right now, those are pretty old, but essentially they can't use past information in order to make future decisions or future outcomes. Then we have limited memory, which can use past memory for kind of future decisions and future actions. So this is kind of like Siri and self-driving cars and that sort of thing. Then we get to theory of mind, and we're not there yet, but I think we're definitely making a lot of strides in terms of like the academics and the research behind it. And this is really a computer's aptitude to understand humanity and engage with humans socially. And then the last one, which is self-awareness, and this really speaks to like a fully conscious AI super intelligent machine. All right. Okay, then we get to the actual mechanisms for achieving, a computer's proximity to humanness, and that's machine learning, NLP, and the robotics, and then the substreams within them. Cool. And I think on a more conceptual level, AI really is an opportunity to engage with the metaphysics of humanity, and that's everything from what it means to be human, what it means to exist, time and space, all those cool and sexy things. So for a long time, we had these old dead dudes who kind of defined what it meant to be human and the metaphysics thereof, and they got to ask questions like, what does it mean to be human, and how do we define humanness? And thankfully they're dead, so it means that AI gives us an opportunity to really interrogate that again and understand what it means for us to be human. And when we have super intelligent computers, does that detract from our own humanity? Yeah, so that's me and my friends, and we're wondering what it means to be human in the face of AI. And really, when AI is the dominant, thought leader, who gets their humanity prioritized and whose humanity gets denied as a result. Okay, all right. Cool. For the rest of this, I guess, talk, when I refer to AI, I refer to the narrow AI. So that's kind of AI as we understand it right now. So we can solve well-defined tasks with lots of data. Okay. So artificial intelligence, very broadly, is a field of computer science and statistics that enables machines or computers to behave like humans or to do human actions. Okay. All right. Then within AI, we get machine learning. So it's a subset of AI, and essentially it uses structured data to make decisions autonomously. Then within machine learning, we get deep learning, which is pretty much what this whole conference is about. And it's a subset of machine learning, but it's really like the onion of machine learning because it has lots of layers, and those lots of layers are just algorithms that are used to get a deeper interpretation of unstructured data. Okay, and then another subset of machine learning, and it has a lot of overlaps with deep learning, is reinforcement learning. And this is also super, super sexy. And I know someone is giving a talk on this, I think, tomorrow or the day after. So definitely go to that. And really the difference between deep learning and reinforcement learning is that unlike deep learning, reinforcement learning essentially dynamically changes, the agent will dynamically change its actions in order to achieve a certain output or maximize a reward. All right, cool. And then getting into what machine learning is and isn't. So machine learning is magical, 100%. It's a lot like science where you throw lots of things together and you get this really wonderful and fantastic result. What it's not, though, is it's not magic. It can't just solve things with the touch of a wand or a click of a button. And I guess to instantiate this, say you have like a set of sushi ingredients or whatever, machine learning can help you to understand sort of what permutations of sushi you can create, or the reverse, you have sushi and it can tell you sort of, what are the combinations of ingredients needed to make that. What it can't do is take a set of sushi ingredients and give you a mermaid, for instance, right? That's just so outside of the realm of what is physically possible. Okay. And then I guess in the terms of like actual, working with machine learning, if you have garbage data and you apply a machine learning algorithm or a deep learning algorithm, you're going to get a garbage output, but it's just going to be fancy, right? Machine learning relies on the data that you give it. So what it can't do is take garbage data and give you gold, right? Actionable insights and decisions. Yeah. So machine learning really is nothing without data, and it's nothing without lots of data. Cool. All right. So a question, or I guess a conversation that I often have with lots of people is that, like, why is machine learning so popular now? Like, where has it been all this time? It's been around, but because we now have the technology that can support a lot of machine learning algorithms and deep learning algorithms, it's now become widely popularized. That and hype culture. So the more people that do it, the more people that get involved in the conversation. And I think there's kind of like a weird glamorization that happens with machine learning. So you're like a machine learning engineer or something, and everyone's like, cool, you write like 3 lines of code, you import from scikit-learn, and you're the best. So I think what often happens in the media is we just see this, right? You see the super popular, super sexy algorithms, and you kind of don't fully understand what it took to get there. Okay. So generally, in order to get to the sexy output, the performance, you need to do a lot of like exploratory data analysis. You need to clean and standardize your data, and you need to understand what it means to clean and standardize it for your particular problem statement. Then you get to the training and testing, which is again the precursor to the sexiness, and then you get your actual predictions and evaluations, which is this. Cool. All right. I'm going to run through a couple of the models. And again, like, don't get too bogged down on the maths and the stats of it. These are really just high-level concepts. And if you do want to talk about it, like, let's grab a coffee or a drink or something afterwards. All right. So logistic regression, which is kind of like the OG of algorithms. It's a really great classification algorithm. And it's super sexy and super popular because it's accessible and it's easy to understand, even if what you're doing is not machine learning on a day-to-day basis. Cool. All right, and it's great because it's able to discern the relationship between the data's features or variables and then the likelihood of its outcome or the probability of its outcome. Okay. It uses something called maximum likelihood estimation, which essentially helps to get your regression coefficients. And this helps you understand the parameters that are needed to give you the result, the observed data. Okay. And then the heart of the algorithm itself is this function, which is the sigmoid function. And essentially what it does is it takes all the kind of linear outputs and it squishes it, and it will give you a number within that range of 0 to 1. So it gives you a probability. Cool. Yeah, and that's it working over there. So you see all the inputs going in, it gets summed up, then it goes through the sigmoid function over there, and then you'll get your output, which is a probability. Great. Cool. Then we get support vector machines, which are also kind of like the bread and butter of machine learning algorithms. They're super powerful and also relatively easy to understand. Okay. All right. So basically what it does is an algorithm that finds a hyperplane in an n-dimensional space to classify data. So this is really nifty if you're able to think in higher dimensions, which I'm not. But essentially what it does is it takes, so a hyperplane is essentially a decision boundary that enables the classification. So if you look at the one on the, what is that, the left, your left, that's essentially the raw data that you have. And then if you were to kind of extrapolate that into a higher dimension, you'd be able to cut it like that. And this is not necessarily useful right now, but if you think about data that is quite spherical, or it's all clustered in like a circle, it's hard to linearly separate that. But if you cast it into a higher dimensional plane, you are actually able to separate it like that. Cool. And the goal of the SVM is really just to maximize the margin distance. And what that means is, so if we look at the left, we see that the distance between those classes, so the green and the blue dots, is quite small. So the probability of a new data point coming in and you correctly classifying it as a blue or a green dot is actually kind of small because they're so close together. Okay, so the smaller your distance, the more likely you are to misclassify your next data point. Okay, so you ideally want to get to something on the right, which has quite a large distance between the points. Okay. And then, yeah, similarly to the logistic, it's a squashing function, and it'll squash it between -1 and 1. Cool. And then that's the cost function that's associated with it, and essentially you want to try and get your cost function to be 0, because that means that your error rate is really small, and what you're predicting is super close to what your observed data is telling you. Cool. Okay. Now we move on to random forests, which are also super sexy. And I think a really important question to ask is like, we have decision trees. They're great because you're able to visualize them. You can actually like draw them out and see sort of what scenarios you're going through in order to get to your outcome, versus a random forest where you're just not able to get that kind of granularity. So why would you actually want to move to a random forest? And the short and sweet answer is that you generally get better accuracy associated with a random forest than you would with a decision tree. Okay. They're also super diverse. They're able to solve for the classification and regression problems. So in terms of classification, this is fraud, this is not fraud. And then in terms of the regression problems, that you have a credit limit that's between a certain range, and there's an R-squared that's associated with it. Cool. All right, and this is kind of just how it works. So you'll load your data and your sexy libraries, and then you'll determine your target variable, which is essentially the outcome that you're trying to predict for. So fraud, not fraud, whatever. And then you'll split your training data, you'll split your data into training and testing. And as far as I know, there's no hard and fast rule as to like what the split should be. Like I've seen some people do like training is 90% and your testing is 10. I've never seen something that's like 50% testing and 50% training. I don't think that's something that's done. But yeah, rule of thumb, tend to have more of your training data. Okay. From there, you'll take your training data and you'll bag it. And really what that is it's bootstrapping and aggregating your data. And this is really important for random forest because it helps you get a larger data set than what you actually have because you're bootstrapping it. And that helps you improve the randomization, which really just helps you get more confidence in the accuracy of your result. Cool. And then from your bag data, you're going to be able to discern your variable importance. And this essentially uses like a voting method. So you'll get all your little decision trees, and it'll tell you across all of them, we think variable B, C, D, B, whatever, was the most important in this model. And you'll kind of sum up all of them, and whichever is the most common variable, so let's say variable B, that is actually going to be that's the most predictive variable, and that's really important. Cool, and then once you're happy with that, you'll do your out-of-bag sample, which is your testing data. You'll run it through the random forest, and then you'll see what the accuracy is associated with it. Awesome. Okay, I'm going to run through neural nets super quickly, mostly because again, this conference is dedicated largely to neural networks, and I think people can do it a lot more justice. But high level, basically what it does is it takes an input, it runs it through some kind of black box magic, and then you get an output. And the really important part of neural nets and why they're so, I guess, famous and so liked is that they rely on the Universality Theorem, which really just says that irrespective of the function that you're using, there's a neural net that can somehow computate or approximate for it. And that's super powerful. Okay. Then in terms of what it is, so it's an application of deep learning. And again, it's also become popular because we have the technology that's able to support it. And there's a couple of different ways to think about it. So there's the somewhat retired brain analogy. You get an input, very much like your brain, synapses fire, and then you get an output. Composite function, so it really just acts kind of like that mathematical relationship. The fact that it's a computing system, and this is the general sort of network architecture for it. And then also that it's a pattern interpreter. So it's able to discern patterns across large sets of data. Cool. This is some of the more high-level but technical stuff associated with neural nets. And the heart of them is that they rely on these activation functions. And picking your activation function is usually one of the hardest parts of the neural net. So if you look over there in that hexagon, those are some of the activation functions that you can use depending on what your data looks like. And without an activation function, essentially all you have is a linear function. Cool. Then I think something that's widely talked about is this thing called backpropagation or backprop. And really all that is it's a recalibration of the gradients for the activation function. So it recalibrates it, and then it reweights and rebiases your weights and bias in order to get to your intended output. Okay. Then you also get your learning rate, which really just tells you by how much should you adjust your weights and your biases. And then the momentum, which tells you sort of how much should the previous outcome affect your future outcome. Okay. All right. So this is the general network architecture. And basically what you have is your inputs over there, the blue dots. Then you have your hidden layer, which is the black dots, and then your output, which is the green dots. And basically what it will do is it's going to sum up all the inputs. And so basically what will happen is you'll take your inputs, you'll times it by your weight, and then you'll add your bias, and you'll get to that hidden layer over here, this gray thing. And then you're going to apply your activation function, which really just squishes it into something meaningful. And then you're going to get this nonlinear output, and it's going to give you your prediction. Okay. Then you're going to use your backpropagation to re-weight and re-bias your weights and your biases in order to get to this intended outcome over here. So you really want to reduce the error rate between what you're predicting and then what's actually there. Okay. And then you can obviously apply the learning rates and the momentums to understand by how much you should be adjusting your weights and your biases. Great. And then you just kind of iterate and make sure you have lots of time and computing power to do so. Okay, so story time for me is the best because my brain doesn't really work in abstraction, so I think understanding formulas and stuff are great when that's how your brain works. It's not how my brain works, so the story time is basically for everyone whose brain doesn't work in abstraction. Cool. All right, so we're going to do just the classical flower classification. So I don't know if you know who this dude is. This is Guido van Rossum. He essentially designed Python. He's the father of Python. And he recently stepped down as like benevolent dictator of Python. And I'm not sure if you know this, but he's currently unemployed and has picked up a passion project, which is origami. He's really good at it. And because he's also really good at data and stuff, he's quite good at collecting sort of the stuff that he does. So in every time he makes an origami flower, he'll write down the length and the width and what flower it is. So if it's a rose, he'll assign a 1, and if it's a tulip, he'll assign a 0. Except this one time when he got drunk and he forgot to say whether or not it was a rose or a tulip. So that's pretty awful, and he doesn't know what to do. But thankfully, he has a best friend called Mr. Model, and Mr. Model is really just an anthology of algorithms, deep learning, machine learning, and etc. And Mr. Model is going to try and help him identify what the flower is. Cool. So in this instance, Mr. Model decides to recommend a neural network in order to classify the problem. And over here, you can see sort of the general network architecture associated with this problem. This is the activation function that's going to be used, which is the sigmoid, similar to the logistic regression. Cool. All right, and then here is actually just the raw data. So the red dots are the roses, and the blue dots are the tulips. And that gray dot over there is the misclassified or unclassified data point. So I think when you look at it vertically, you can say, oh, this is obviously a rose. But if you look at it horizontally, you could be like, oop, that might be a tulip. So he's in a bit of a pickle. So yeah, okay. Again, this is the network architecture associated with the neural network. This is the sigmoid function. That dark green line is the sigmoid function, and this olive line, I guess, that is its derivative. Cool. This is all the boring code that you can use to build your own very simple neural network. There are obviously some sexier libraries that you can use, like TensorFlow, Keras, PyTorch, all of that. But really all this is telling you is, there are weights and there's a bias, there's iterations, and then there's a learning rate and your cost function associated with it. So over here, this is our cost function, and what we want is for it to go down, because if your cost function goes down, it means that your predicted output is very close to your actual output. So over here, we can see that that is, in fact, what's happening. Cool. So when all is said and done, we eventually, we predict the outcome, and so anything that's very close to 1 means that it's a rose, and anything that's very close to 0 means that it's a tulip. So in this case, we predicted, the output prediction was 97%, so because that's very close to 1, it's probably going to be a rose. Okay. And then this is sort of, if we were to just plot out all the possible data points associated with this, we can actually see that we did plot this correctly, and it is actually in the rose space and not the tulip space. Now we're going to do something called fraud classification. So because his origami business has become so successful, he's actually offering credit. So you can lend money from him in order to buy some of his origami. And that's really exciting because he's unemployed. Okay, so now Mark Zuckerberg comes in and he's like, hey dude, I really want to buy some origami flowers, but I have like no money. Please lend me some. And basically Guido's like, no, I'm not going to lend you any money. And Mark is like, well, dude, what the hell, why not? And he's like, well, you're a lizard man, you're not a real man. And so basically what's happening is he thinks that there's a case of fraud, and he's trying to come up with a way to understand what cases are fraudulent and what are not fraudulent cases. Okay. And that's exactly what we see over here. So this class over here refers to whether or not something is fraud, given the data set that it's associated with. So something is not fraud if it's got a 0, and something is fraud if it's got a 0, and it's not fraud if it's got a 1. Okay. And here I think because Guido's got lots of time on his hands, he decided to try 2 models associated with this problem. So he decided to try neural networks and then random forests in order to get to the intended outcome. And now he's sitting with the problem like, all right, cool, I did this, which model is the best? And there are a couple ways to get your prediction output and to visualize them. But he used a classification matrix, and he also used a confusion matrix and a classification report. So over there and over here, you can see all the ones that were correctly classified, and you can also see the ones that were misclassified. And then over here in the classification report, it's pretty much the same as the confusion matrix. It just looks a little bit better, or it's easier to read. So for the neural network, we can see that it correctly predicted everything, basically. And in the random forest, it misclassified maybe one or two things. So the overall precision rate is lower than the random forest, the neural network. So in this case, I think Guido would be like, cool, let's use the neural network in order to predict fraud cases going forward. All right. Yeah, so I think this speaks to a larger thing, which is really trying to understand which model to use when it's appropriate to use a model given a set of constraints that you may have. All right, so I'm sure you're all aware there's a wonderful new TV show that's come out called AI's Next Top Model, and it's being hosted by Tyra Banks, who is an AI expert. And essentially what she does every week is, these models come through and they have to go through a series of competitions, and then they get voted out until there's only one prevailing AI model. Okay, so I'm sure you guys saw last week's episode. Final two, Annika and myself are the modelers. Annika decided to bring forth the random forest, and I decided to come through with the neural network, and we presented it to Ms. Tyra Banks, and she had the hard task of deciding which model is the best to use forever and always. Okay, and there really is no simple answer which model you should use every single time. There are trade-offs associated with each model that you use. And the problem with testing multiple models on the same set of data is that it can actually just lead to overfitting. So you're not able to fully generalize your problem or your solution because it only works for that particular data set. Over and above that, training lots of models is super time consuming and resource intensive. And depending on what kind of work you do, you might not have the luxury of time. Okay, so I think what is super important to work on is your features or your variables, and then make sure that your data is the best possible data you have. And I guess this is really important when you're in corporate. I think when you're doing analytics or model development or something, you can often just be the custodian of that model or those analytics, but you also have to be the custodian of that data. So if there's something wrong with the data and you know about it, you absolutely need to do something or find someone who can do something about it. If there's a big system change and it changes the way in which your data comes to you, so previously you were getting raw data and now you're getting rolled up data, that's going to affect a lot of how you think about your problems going forward. So make sure you're in the loop when it comes to those conversations. Cool. Then also just in terms of understanding the effect of your false positives and false negatives, like how much do they actually matter? So in the context of natural disasters, for instance, so if you're predicting a natural disaster, you don't actually want to incorrectly predict that there's not going to be a tornado and then there is a tornado because people die and that's bad. If, however, what you're doing is Guido's passion project and you're just predicting flowers, maybe it doesn't matter too much whether you predict a tulip or a rose because probably no one will die from a paper cut. Yeah, so it just really depends on kind of what you're doing and who you're doing it for. Okay. Then some general tips and tricks that I've picked up. So as I said at the start, I'm a humanities baby, so I've never done coding before, but I can tell you that coding is not the hardest part of learning AI. The hardest part of learning AI is really understanding the problem statements that are associated with the thing you're trying to solve for. But a really good way to get into AI is to come up with passion projects. So what is it that you like? What is it that you enjoy? And how can you align what you like and enjoy to an AI method or something like that? Kaggle is a really good platform. I don't know if you guys know about Kaggle, but it's essentially a competition platform online. And it's a really good place to get started in terms of like machine learning and deep learning and stuff. They'll have competition data sets, and there's like sometimes there are prizes associated with it, and you really just work on this thing for however long you submit your findings, and then if it's really good, you win. If it's really bad, I mean, you don't lose, you win knowledge, and that's important. Cool. All right, online learning is amazing. I think the best online learning resource I've ever come across is Stack Overflow. It's so much better, well, not so much better. I think it's a lot more engaging than some online courses that you'll do, just because people respond really quickly. I haven't come across a problem that wasn't already on Stack Overflow, which is really affirming. I think when you think of a problem in your head, or when you think you don't understand something, it can make me feel like I don't really know what I'm talking about and that I'm somehow stupid. But then I go on Stack Overflow and I see 200 million people have posted the same question, and that's really affirming. Oh, sorry, just on that, some of the really good online learning platforms in addition to Stack Overflow are Udemy, because they're some of the cheaper options, so it makes it a lot more accessible to you. There's Udacity, which it tends to be a little bit more expensive, and Coursera, which is also expensive. Yeah. Cool. Meetups. So I don't know if all cities have meetups. I know Cape Town and Joburg have a lot of prominent AI and machine learning meetups. I don't know if Durban does. Does it? Okay. If they do, definitely get involved. But meetups are really cool because you get different speakers who do different things, and they present on what it is they're doing, what they're struggling with, and you can engage with them either during the talk or afterwards, and there's usually the promise of beer and pizza, so it makes for a nice social setting. Cool. Human people are so important. I think don't negate the importance of like speaking to other human people who are not doing data science or AI. I know this morning we were talking about kind of the cross-disciplinary interactions and why it's so important for people who are super technical or who come from a STEM background to engage with, humanities babies and stuff like that, because I think it really helps you understand your problem, and it also really understands who you're solving things for, and that's helpful. Okay. This is particularly related to corporate. I don't know how it works in academia and research, but in corporate, you can come up with a really cool, sexy algorithm or model that can solve pretty much the whole problem. But because your systems and your infrastructure can't support that, your technology is not at the right place, you actually can't implement it. And it's not that you've wasted your time, it's just that you actually haven't done your job. So I think be mindful. Be mindful of the current state of your system and your infrastructures, and then be mindful of where it's going. So if you know that the system, we have a lease on the system for 5 years, and after 5 years we can move to quantum computing, then make sure that you have a solution that can be dynamic enough to switch from those types of systems. Cool. AI ethics, super, super, super important. Again, I think in corporates, oftentimes what you're trying to solve for is, or maximize is profit. You want to make sure your profit is the highest without getting too much losses, and that's, it's a relatively simple problem statement, and there's so many ways to solve for it. But oftentimes just making sure that your profits, or getting to profits, is efficient means that you can hurt people in some really awful ways. So be mindful of the ethics that are associated with AI, get involved in those conversations if you can, and yeah. Thank you very much.
Okay. My name is Mehawa, and I'm a student at UP. So when you presented, you showed support vector machine, I don't remember the other one, but you only explained on classification. So that means I cannot do regression with support vector machine.
Is your question on support vector machines that you can only do classification with them and not regression? I think theoretically you can do regression. I don't know of anyone personally who's done regression using SVMs. Yeah.
My name is Justine, and I saw one presentation where you use one slide where you use the neural nets and then the forest. And then you're like, okay, where you have accuracy, was it one? I think it was 1 and then 0.9. And then you're like, okay, where there's perfect predictions, then you're good to go. That's the best model. So, but how sure are you that we're not really overfitting? So, well, I'm just looking at the numbers and I'm like, okay, how do I say this is the best model without literally taking a model that is overfitting my data?
So I guess first thing, disclaimer on the data set that I used the famous, the iris data set? Yeah, the iris data set, which is perfect. So, but I guess in real world terms, like, this is probably something that you're going to have to pick up when you do your EDA, your exploratory data analysis, to understand, like, does this perfect precision make sense given the underlying data? So you have to be super, super close to your data, and you have to understand, I think, the systems that get you your data and understand sort of where it's dropping off and things like that. So I don't know that there's a hard and fast rule in terms of like the statistics associated with testing whether or not something's fitted. But yeah, I would personally say just make sure you understand your data, and you can very quickly understand whether you are overfitting or whether you're underfitting.
My name is Takudzwa. I'm a student and I'm studying statistics. So from a statistical background, we usually use like linear regressions for prediction. So do you see neural networks and random forests like phasing out those type of linear models?
And I think it really depends. One thing I've noticed when you speak to people who like do AI or in machine learning and stuff is that there's like a glamour factor associated with how complex your model is. And sometimes all you need is a linear regression to solve for a particular problem. So if it's appropriate, use it. So I don't think random forests and neural nets or any of the sexy new algorithms are going to replace it if it still has value in that particular situation. I think oftentimes the issue with linear regression is that the world is not linear, and that's why it doesn't facilitate a meaningful insight or meaningful answer when you use it. And that's why some of these models which accommodate for nonlinearity and complexities in data, I think that's why they're becoming a lot more important. But I'm a big fan of linear regression, so yeah.
My question is, earlier on during the panel discussion, there was an issue that was raised, not an issue as such, but they said we could use machine learning techniques to answer the question of causality, causal inference or causality. I'd like to know how we can embrace machine learning when we try to answer questions of causality.
I don't know if machine learning in the sense that there are algorithms necessarily that are going to tell us this is a causal relationship versus this is, you know, something that is just correlated. I do think, however, that machine learning and the associated methodologies around it is going to help us create more lateral solutions and lateral thinking. And I think a big part of the problem is that as humans, you see something and you try and explain it with the immediate things around it, and that's already the problem, right? That's already a bias. You're already assuming that there is an answer to something instead of it just being correlated. So I don't know that there's an algorithm necessarily that's going to support in a statistical or definite way that this is causal versus this is correlation. But I do think that the more you engage with these kinds of thinkings and methodologies, the more you're going to come to appreciate that, you know, I don't know what I'm saying. Let me start again. I think the more time that you spend doing like machine learning and AI, you're going to be able to understand or get a deeper appreciation for nonlinearity, and then the models will kind of come as a result of that. Yeah.
So I know you from ABSA, so I just wanted to ask if you have any tips for other corporate banking, because we're from Nedbank. And it's like all this AI and machine learning, it's like all the buzzwords, they're always, this is what we want, everything must be machine learning, and then you try present it to them and they're like, Python's out of policy. And then yeah, so do you have any tips?
And I'm also super new to banking, but I think what's really helped me is kind of having someone who supports you. So, and that oftentimes needs to be your manager or a manager, just someone who actually has, you know, power in meetings and can influence conversations in particular ways. So I don't want to say flirt with your manager, but, you know, show up for them. Show up for them in real. I don't flirt with my manager also. Like, I'm so sorry, that sounded awful. She's married. So I think you need to definitely develop the relationship between your manager or your manager's manager, just anyone who's really in the room when these kinds of conversations about policy, systems, etc. are being had. And I think that's half your work done. The other thing is, I guess, proof of concepts. I'm sure, as you know, banks love proof of concepts. When I first started working at ABSA, they were like, oh, we're doing this POC. And I was like, person of color? What is this POC that you're talking about? But yeah, proof of concept. So if you do have time, which I know is hard in a bank, but if you have time to literally solve a problem using AI or anything sexy, do that and bring a couple people into the room, tear it apart, put it back together, and show them the uplift. In terms of the systems though, so also we can't use Python. We use SAS, which is not, it's fine. But I guess for me, when I was struggling to move from Python to SAS, I think because a lot of times you rely on the libraries and the functions that are built in, scikit-learn, whatever, it means that you can be kind of lazy because you don't ever have to build the things yourselves. But if you can build the thing yourself, it means that you can put it into SAS, or you can put it into whatever programming language you're using. So I think that's really, really important. What else was I going to say? So ABSA, I think, is also in a bit of a precarious position, and in the sense that we're losing market share in some areas, and so now we're scared into doing things. There's also there are new fintechs coming out, there are new banks coming out that are really shaking the market, which means that banks can't actually be complacent in the way that they do things anymore. So you have to come up with sexy things and get new people who think very differently. And I think if that's where you guys are, and if you're in a team that makes a lot of profit and gets a larger training budget, then you maybe also have some influence there. So I think for me in particular, home loans tends to be one of the most profitable divisions in a bank because homes are expensive. And so our CRO is really great because he puts a lot of time and effort and money actually into upskilling people. That wasn't really a tip or a trick, that was an anecdote, sorry.
My question is, in your presentation, you mentioned that no one has used 50% testing and 50% training. I don't know whether you actually. I didn't hear you say maybe the best, because I've read some where people use maybe 30% and 70%, 20%, 80%. So what would be your take on that? And then, are all models able to handle all types of data? Because I have also read some things which said some models probably testing SVM and then random forest, testing. Okay, I'm from the environmental science background, so people classifying trees and forest using SVM and then using random forest. And they based on what they do, sometimes they recommend SVM above random forest. Depending on this is able to handle this type of data, this is not able to handle better this type of data. So that's the reason I'm asking the other question.
So just in terms of the train test split, so you probably didn't hear me because my mic was far away. But yeah, so as a rule of thumb, I don't know if it's a hard and fast, you have 90% of your training data and 10% is left to testing. I do know, however, that you don't have an even split of testing and training data. And I think this is largely because it's easier to overfit in that instance, right? but also I think it also depends on the size of your data. So if you just don't have a lot of data, then maybe you're going to be a little bit more lenient on that train test split. I personally, like when I've done stuff, I like the number 7, so I like to do 70-30 splits. But I know lots of people who also do 80-20. I don't know anyone who's done 90-10. But yeah, I think as much as possible, you want to get most of your training data, or the majority of your data needs to be your training data, and a small portion of it needs to be your testing data. That was the one question. The other question was about understanding, so in terms of which model when, I think you were giving the example between like when you're classifying something, some people recommend SVM, some people recommend random forest, and how do you know which one to use? So I know like a lot of the what do you call it, like online platforms will tell you, these are the pros and cons associated with this model. So definitely look at that, use that as your how-to guide. It usually comes down to, especially when you're looking at structured data, how noisy is it? And there are some algorithms that are actually really good at working with noisy data, and some that just aren't. So like KNNs, for instance, they just don't account for outliers. So if you have lots of outliers and you have like lots of noisy data, it's probably not the one to use for you. Random forests, for instance, this is interesting. I've done a couple where like the data has been super random and super noisy, and the one gave me like a pretty fair result, and the other one gave me just the wildest result. And when I was asking someone about it, he was like, "Oh my God, your data is disgusting. It's so noisy. Like, no wonder these trees have no idea what's going on." Yeah, so I guess a hard and fast rule is just read up on the model that you're using or thinking of using, understand how noisy your data is, and how well can it accommodate for it using like regularization or something like that.
Sorry, I suppose just to add to that maybe a little bit on the split technique as well, and how much data you should split out. There are also other techniques where you can do things like cross-validation, where you kind of break your whole data set into 10 pieces, and then you train on 9 and test on 1, and then you train on the different set of 9 and test on 1, and train on a different set of 9 and test on 1. And you can repeat that process again and again and again, and then you can assess kind of the accuracy of your models over all these different combinations of training and testing portions. So that's one really, really useful way of doing it. And then the other thing of which model to use, I think that's a big argument for really understanding how the models work, right? And there's always this temptation when you've got libraries that implement everything for you to just go, scikit.train neural network, KNN, random forest. You get the library to just train all of these different models and then see which one works. But it is important to fundamentally understand what the method is doing and when the method is going to do good or bad with the data that you've got.
Yeah, I 100% agree with that. I think for me as well, because I have this glaring imposter syndrome, like I'm super wary of using functions and libraries that I don't understand, because I imagine just a whole room of people is going to be like, how does this thing actually work? And I'm going to cry because I won't know. So I think if you can, try and build as much as possible by hand, just so you understand like the different phases of what's going on, and at what point are you finding like this point of inflection, and at what point are you actually just, squashing things. I know people love to hate Microsoft Excel because it's the worst, but it's also the best, guys. And I think you can do a lot of the steps in some of these fancy models in Microsoft Excel and really understand like what it's doing, why it's doing that, and tweak it a little bit, and then go for your sexy libraries.
Any more questions? Okay, well then let's give Kerryn a huge round of applause. Thanks, Kerryn.